Our first topic is about AVL trees, splay trees, and amortized analysis. So let's check them out one by one. We're going to start from AVL trees. So what is the first natural question to ask whenever we have to learn a new concept? The first natural question should be, why do we have to learn this, right? So the target of AVL tree is to speed up searching. To be more specific, to speed up dynamic searching. Dynamic searching means we're going to have insertions and deletions happening all the time. So the data set is not fixed, it's dynamic, right? To handle dynamic searching, we have already studied a kind of data structure in the fundamental course. Do you still remember? That is the binary search trees, right? So here's a quick review. In a binary search tree, first of all, it's a binary tree, and all the keys in the left subtree will be smaller than the root key, while everything in its right subtree must be larger than the root. All right, and therefore, if this tree is perfectly balanced, for example, if it is a complete binary search tree, then the time complexity for all the operations like insertions, deletions, or find will be proportional to the height of the tree, right? And if it's a complete binary search tree, the height will be big O of log n, so everything will be perfect. However, the problem is that although the time complexity of all the operations will be proportional to the height of the tree, but the height can be very bad as a linear list, right? So for example, if we insert those keys in increasing order, what's going to happen? We're going to obtain a tree that will skew to the right, right? Increasing order means root is the smallest key, and then it gets larger and larger, and finally obtain a tree that is skewed to the right. So it's no longer really a binary tree, but rather a linked list. So in other words, the tree structure depends on the input sequence. For example, here, let's consider the months from January to December. If we enter these keys from January to December, this is the resulting binary search tree we have, right? Well, January comes first, so it will be the root. Then February, F is smaller than J, so February is here. And next will be March. M is larger than J, so March is here, and so on and so forth. So this is tree we obtained by entering from January to December. And this is a balanced tree. Notice that it's not a complete binary tree, but still it is quite balanced. And the average search time of this tree is 3.5. Average search time means, for example, in order to find January, we need one comparison to find it, right? Say in order to find December, it's going to take 1, 2, 3, 4, 5 comparisons to finally find this December. So average search time is to sum up all the search times and divide it by 12. And this is number we obtain. And how about this balanced tree? Why don't you just click on the screen to pause the video and take a few seconds to do the calculation. Okay, so the average search time of this tree would be 3.1, a little bit better than this one. And how about a skewed tree? What if we sort all the months in alphabetical order, say increasing order or decreasing order? The average search time for the skewed tree would be what? Would be 6.5. Quite bad, right? So the next question would be, how can we obtain a balanced tree like this? There are basically two directions to think about. One direction is that can we simply carefully design the input sequence? So if we don't input January first, if we input July first, and February next, and so on and so forth, if we can carefully design the input sequence, then hopefully we can obtain a quite balanced tree. But I have to say that this is not a realistic solution. Because what? Because life is like a box of chocolate. You never know what's going to come next, right? We're talking about dynamic searching. It means that the new element will keep coming. You never know what's going to come next. So it will be impossible to rearrange the input sequence to obtain a perfectly balanced tree. On the other hand, if we can rearrange the input sequence, why don't we simply sort them in, for example, increasing order and co-binary search? It will be much simpler, right? So this direction doesn't work. The other direction is the AVL tree direction. That is to keep the tree dynamically balanced. What does it mean? It means that let's keep an eye on the tree. If the tree gets unbalanced by some new input element, let's do something to rearrange this tree to make it balanced. And this is the idea of AVL tree. AVL tree is named after their inventors. They are Adelson-Welsky and Landis in 1962. And they were the first dynamically balanced tree being proposed. And here's the definition. We call it a height balanced tree. First of all, if a tree is empty, then it's considered to be height balanced. If it's non-empty, and we say it's height balanced if and only if its left and right subtrees are both height balanced. So it's a recursive definition. And their heights are differed by at most 1. So this is basically the definition of an AVL tree is height balanced. For an empty binary tree, the height is defined to be -1. So to implement an AVL tree, one way is to keep an eye on its BF. BF is not boyfriend, it's the balance factor. Okay, we define the BF of any node to be the difference of the heights of its left and right subtrees. So it's the left height minus its right height. So in an AVL tree, if everything is fine, the BF of every node should be either -1, 0, or 1. Now here's a quick test to see if you really get it. How about this one? Is this one an AVL tree? And the answer is no. What is wrong? If we only look at the root, it's fine. The BF of the root is just 0, but its left subtree and right subtree are both not okay. How about this one? This is perfect. Okay, how about that one? The answer is no. So which one is not balanced? The root, right? Okay, so the idea of AVL tree is that we always keep an eye on the BFs. And if there's a signal that something's wrong, we would like to do something to rearrange this tree, so to make the resulting tree balanced. And that something ought to be quite simple. Let me explain this by an example. Let's, again, input the months. Okay, so the first one is March. It's perfect. No problem. Next one, May. Notice that when May comes in, the BF of its parent should be updated. It's no longer perfectly balanced, but still, it's okay. Next, let's input November. Then something is wrong here. It's no longer balanced. What can we do? Just make a simple rotation. It's called a single rotation. Rotation means to rotate this node down to be the left child of this node in the middle. So it will be a perfectly balanced tree. So what is the rule here? in general, we see that this troublemaker is November because it's the insertion of this node that caused the unbalance. So the troublemaker is in the right subtree of the trouble finder. The trouble finder is March. March is called the trouble finder because this is the first node that signals the trouble. And because the troublemaker is in the right subtree of the trouble finder, therefore this is called an RR rotation, right, single rotation. In general, if we are before the insertion, if we have this situation, and then we make an RR insertion, this is going to be the result of RR rotation. We rotate A down to be the left child of B. But if B had a left subtree before the rotation, what can we do about this left subtree? Think about it. Okay, we should put it here. Okay, make the original left subtree of B to be the new right subtree of A. Why does it work? The point is, after the rotation, it must still be a binary search tree. So is this the correct position for the left subtree of B? Let's check it out. So before the rotation, since this is the left subtree of B, it means that it's smaller than B. And this is in the right subtree of A, so it must be larger than A. After the rotation, it's the right subtree of A, so it's larger than A. And it's in the left subtree of B, so it is smaller than B, so everything is fine. So this is a single rotation. One thing to be noticed here is that this A is not necessarily the root of the tree. It can be the root of any subtree. Okay, let's continue. Next, let's input August, so everything's fine. Next, when April comes in, there are two signals. So tell me, which one is the trouble finder? So here comes your first discussion question. What can we do now? So I would suggest you to, click on the screen and pause the video and think about it for a minute. And then when you come back, I'll show you the answer. Everything is just symmetric. We just do a clockwise rotation. That will solve the problem. Since this troublemaker is in the left subtree of this trouble finder. Trouble finder is the first node that signals the trouble, because all the BFs are supposed to be updated from bottom up. Therefore, March is the first trouble finder. Okay, since April is in the left subtree of March, this is called an LL rotation. Make August the new root and rotate March down to be its right subtree. So in general, it's very simple. It's everything just symmetric. If we make an LL insertion, that will be the result of an LL rotation. These are the simple cases. Let's continue. Next, when January comes in, we see that May will be the trouble finder, and January, the troublemaker, is in the left subtree's right subtree of May. So this is called an LR rotation. Again, we need to make a rotation. And the result will be like this. What happened? It looks quite complicated, but it's quite simple. We just pull this node up to be the new root. March will be the new root. August is still here. And the original root, May, will become, is going to be rotated down to be the right child of March. So in general, if this is the original situation and we make an LR insertion, the new node can either be here or here, it doesn't matter. Anyway, A will be the first trouble finder. So what we do is to pull this node up to be the new root and make A its new right child. This is the result of LR rotation, and the original left and right subtrees of C will be assigned to B and A respectively. So to make sure that the resulting tree is still a binary search tree. And this kind of rotation has another name. It's called double rotation because it can be considered as the combination of two single rotations. Rotate march up and then up. After two single rotations, we can obtain the same tree. So it's also called a double rotation. Now let's move on. When December and July comes in, everything is fine. Next troublemaker will be February. When February comes in, what can we do? So first tell me, which one is the trouble finder? August, right? Because it's updated from bottom up. So August is the first node that signals the trouble. Then we just look down 2 levels, starting from August. So the troublemaker, February, is here. It's in the right subtree's left subtree of August. So again, everything is symmetric. This is the result of an RL rotation. What happened is that we pull December up to be the new root of this subtree and rotate the original root, August, to be the left child of December. In general, again, everything is symmetric. If this is the original situation and we make an RL insertion, so A will be the first trouble finder, and the resulting tree will be like this. Pull C up to be the new root and rotate A down to be its left subtree and reassign its left and right subtrees. So basically that's all about AVL tree. Let's continue to do more practice. Alright, let's now insert June. So March will be the trouble finder. What can we do now? I would suggest you to click and pause the video and try to solve this one, and then let's compare the answer. These are the only 3 nodes that we should care about. So it's a typical left-right rotation, and that will be the result. Have you done it right? Okay, let's again input October. This is simple, right? So that will be the 3 nodes that's supposed to be rotated, and that will be the result. Okay, next, September. Notice here that even though we don't need to reconstruct the tree, even though everything is fine, still we have to update the BFs from bottom up. Okay, but let me remind you that BF is only one way to implement the AVL tree, and there are other different ways. For example, another option is to keep a height field instead of BF for each node. So just test by the definition of an AVL tree. The detailed implementations are given in a textbook. One last question. Say, obviously we have that the time complexity of every operation is proportional to the height of the tree. But what is the height of an AVL tree? The answer is not so obvious. We hope that it could be big O of log n, but it's not clear so far. So let's take a closer look. Say, suppose we have a height balance tree of height h. Then let's denote the minimum number of nodes by n sub h. So n sub h is the minimum number, notice here, is the minimum number of nodes in a height balance tree of height h. Then this tree with minimum number of nodes must look like either this or this, right? They must not be perfectly balanced because we're talking about minimum number of nodes. Then what is the relationship between the total number of nodes and the number of its subtrees. We have this recurrence equation, right? So n sub h is the total number in this tree, is 1, that is the root, plus the smallest number in its one subtree plus the smallest number in its other subtree. Does this equation look familiar to you? I hope the answer is yes. It looks so similar to Fibonacci numbers, right? This is the definition of a Fibonacci number. The difference is that there is an extra 1 here. Actually, we can prove that the hn is the h plus second f minus 1. So according to the number theory, we know that the ith Fibonacci number is approximately a constant times another constant to the power I. It's an exponential function. And therefore, we obtain that n sub h is approximately a constant times a constant to the power of h plus 2. That plus 2 doesn't matter, it's another constant, right? So basically, n sub h is approximately some constant to the power h. And therefore, we can take a log to both sides and prove that h is indeed big O of log n with some strange base. But that doesn't matter, it's only a matter of constant. So the good news is that with AVL tree, the h is guaranteed to be bounded above by log n.